So you've seen what ParaView can do, right, in the visualizations. So what we're doing now is to give you another options for you to use just in case you know you don't like ParaView or something like that, or whatever your reason is. So, but I think the choice of using whatever visualization toolkit should be whatever that works for you, you know. So, but it's good to. One thing I realize is when I use ParaView or Visit, it really depends on what kind of data that you want to use. So let's say you want to use astronomy in astrophysics. I think Visit is slightly better just because there are a lot of the astronomy data. People running astronomy research and simulation, they use Visit. So with that, what that comes with is Visit is more developed. Since it's open source, the resources to develop toolkits is definitely limited. So if you get more requests from more users on a specific function, which one do you implement first? The one that get most requests definitely got implemented first. So if your community is huge in using one type of visualization toolkit, you want to maybe try to stay with that, because then your support will be a lot better. For example, if you go to a conference, and all your peers, when they render out something, they have this type of labeling, So if you want to duplicate the same thing, if you use the same tool, it's going to be just that much easier to do. ParaView can do the same thing, but you said that you probably have to bend over backwards to accommodate what you want to do in another toolkit. So that's what I'm getting at. See, even the slide that you see now, interactive GUI is almost a duplicate. I can change the word visit up there and do a ParaView. It's going to be just the same. So they both are GUI that stands on top of VTK. So at the underlying platform, and the underlying core engine, they're all the same. So another thing to consider between visualization toolkits is data format. Okay, if you had to go down, and write your data, and load it to the visualization toolkit, then it's really a lot of work. So if you can find a visualization toolkit that can load your data the way it is, it's just going to be that much easier. So if you have to start converting to VTK format, then there's a lot of work. I'm pretty sure that Greg will show you some of how to do it, and it's just going to be a lot of work, okay, at the beginning. But once you get that out of the way, then everything is smooth sailing from that point on. So Visit is funded by DOE for the past more than 10 years. So people has done a lot of work with these toolkits. So a little bit of background is, so they even update some of the VTKs, but thankfully recently they merged, they update whatever, back to KitWest, VTK, so everything is in sync now. Whatever behavior you see on ParaView, you will probably get it in Visit, you probably get it in ParaView as well. So this is where you go to download it, and they have tons of documentation, tutorials, and sample. They even have a Visit user wiki that you can go, and then the forum. So it's good if you want to use Visit, regularly. I would suggest that you sign up for the mailing list. You can ask questions. People there are great. If you have questions, they probably respond to you in like, I don't know, 5 minutes, 10 minutes. But definitely not days. If you ask something and it took days, that means that nobody knows the answer. So I don't know. So same thing, because it's VTK based, so these are the very similar data type, So you have unstructured grid, structured grid, molecule, polygonal, AMR images, time series reports and all that. And I have not used the movie player, the animations creation part of ParaView, but I've used those in Visit. I think because of what the community, the astrophysics community. So with astrophysics, the typical visualization pipeline is they run the simulation of galaxy, in a supercomputer, and then they have a whole bunch of data. And then what they do next is they run Visit to visualize it, to set up the region that they like, and then they use Python, scripting to run through the entire data set, maybe like 1,000 time steps to create image out of it. And then the next step is they want to make a movie out of it. So this is the entire pipeline. Because of that, Visit has everything built into the GUI part. So you can use the same scripting capability is also in Visit. So you can capture, record all your mouse click button. Every mouse click on the GUI can be turned into a Python script that you can automate. The reason for that is you can run it without running the GUI and then use the supercomputer, get like 32 cores, however many nodes you need, and then you generate your images. And then with that, you can bring it in, and start playing with different angles, how you want to create a movie, and then you click a button, then you got a movie. So this is what they do. Okay. So, but the mentality of visualization between ParaView and Visit are a little bit different. I mean, maybe the school of thoughts, how you approach visualization, they are different. They also have visualization, different plots, different operator, same thing. But when you load your data, the only thing like very different from ParaView is that when you load your data, you don't get anything at all. Okay? So Visit expect you to load terabytes of data. So it's not feasible for you to draw something on the screen right away. So you want to set up your filtering first, and then make just a sizable, very small size, a subset of your data to visualize, and then you can apply, then it starts to draw. If it starts to draw everything when you load your data, then the GUI will be so unresponsive that people thought Visit is dead or something like that. Okay, so this is basic GUI. So I think I agree with what Anne mentioned. ParaView's GUI are probably more advanced looking than Visit GUI, mainly because Visit, I think it strives itself as a backend type, command line processing to generate images. So it's very strong in that regard. You set up your Python GUI and you run Visit.cli, and then it runs. You generate your movies over the weekends. So I've done like terabytes of data, running it over very high resolution volume rendering, submit the job and let it run over the weekend, and comes Monday, you get your images. Then you can use FFmpeg to maybe compose it, or you can use Visit to compose it to do your movies. So these are the basic. So the GUI is completely different than ParaView. So you have open file menu, control menu, So the goal here, I don't know, so what is your goal coming here today? Do you want to know a little bit of Visit? Because there's so many, from that point of view, there's a lot of functionality. There's no way that we can touch all day in 1 hour. So what I want to do is maybe, what do you want to get out of this hour? I can talk more at a specific area that you like. So that the goal here is to get you started with your own data, like what Anne said. There's no point going to the slides. You can read the slides. This is not what we are here to do, going through the slides. But I want to show you, if you have questions, what you want to do. So just to get you started. And then there's so much more, and point you to the right direction, information, or you can ask me, stuff like that. And I also want to add another thing about the VisLab. So I think we have a project here with Intel doing real-time ray tracing. So eventually we want to, once that project gets reasonably in shape, we want to provide that interactivity visualization with ParaView and Visit at the VisLab. So one of the devices that we did there is so VR is big. So with VR, it doesn't mean VR is big. VR actually from a scientific visualization point of view is actually what we call immersive visualizations. So with immersive visualization, it gives you ability to look at 3D structure, especially streamlines. If you have complex streamlines, how do you know which one is in front, which one is in the back? So virtual reality technology with immersive visualization can give you the ability to differentiate between what's in the front, what's in the back. Basically, let you see the structure of your data in the three-dimensional space. So this is the added advantage of virtual reality. And it doesn't come free, but with ParaView, it has a plugin called Immersive VR plugin. So with that, I think it's lower the technical requirement for you to get into immersive visualization without having to, run another program, all you have to do is just run ParaView and then run it in the immersive visualization mode, and then you get all that for free. All your filters still works, all your visualization, you just get that. So in the lab, we're going to set up a Z-Space system, which has all the bells and whistles of a virtual reality system that you can come and try. So if you think, of course, you can generate movies out of your data, but the movies, you can only do one angle at a time, or you can, do a 360 movie, 360 different movie from 360 different angles of your data, or you can run through all the data. Or what you can do is run everything in real time, and using the real-time ray tracing plugin together with immersive VR plugin, you can actually get immersed in your data using the Z-Space system, which is semi-immersive. Then you can look at different angle, whatever angle that you like from off your data. So this is something that we would like to offer at the VIS Lab. So come to the VIS Lab, look for me. I'm usually there on Wednesdays. So just I can show you the system the way it is now. But we are working on improving that to add more capability and functionality to it. Okay. So the noise data is just, if you install Visit, download Visit, install Visit, it comes with a sample data set in a directory called data. So the noise data is actually in there, noise.silo. Silo data, I think the silo data format is probably the most developed data format for Visit. Most of the Visit developers, they like to use that. Okay. And then, so I think the main value of this tutorial is for you to start using it. Just download the data, open it, use Visit if you like, and see for first hand, just sort of like get you started with using the GUI, then from that point on, it's so much easier for you to find out, what are the other features of Visit that you want to use, what kind of visualization that you want to achieve. Then when you start asking the question, it's easier for the community to help you or for us to help you. Okay. So we're going to do contours. So the visualization are the same. They all use the VTK in the background. You can do isosurfaces, you can do glyphs, you can do streamlines, you can cut and slice, all that, or whatever you get in ParaView, you can probably find an equivalent functionality within Visit as well. Okay, so I'm going to move over to the live demo now. So if you do a file open, so when you install Visit, it's going to put it here. This is on Windows, by the way. So because I don't think they have I have 10.10. They don't have a binary for 10.10 on the Mac. So, and I don't have Linux installed. So if you scroll down to Silo and click OK, and then so there's a question on the chatbot asking the parallel part. So the parallel part from the user perspective is actually exactly the same. Just from the administration of the software package is a little bit different. There's more setup to enable parallel to ParaView or Visit to use the parallel capability of it. But I think you should definitely tap into that. So you have access. So Greg, can anyone just start a client server session with ParaView or Visit and connect to Stampede or Maverick?
Not from outside. We'll talk about that later.
Okay, good. Yeah, so definitely this is something. But if you nowadays, a 12-core machine, 128 gig in your lab is probably a common thing. You can even set the machine up. Then you can connect to the machine from your laptop. So the goal of that is to run it in a parallel way so that you can harness all the compute power that you need. So with Visit, when you load the data, all it's actually doing is nothing. See, you don't get anything. So, but you can test and see. One thing you should test and see, all this information should be there. So if you don't see this, that means your file is not getting loaded. Or Visit doesn't understand what your file format is and all that. Okay, so these are the different slides talking about opening and closing the windows. Okay, and so from that point on, you can even look at the different ranges of data. You know, what kind of variables? All these are the different variables, scalar variables, you know, and the vector variables, you know. So you have to make sure that your variable get loaded. If not, then your something is wrong with your file format, you know, or the reader or something, you know. You never know. Okay, and then from that point on, okay. I've never run visit with this low resolution. So I'm not even sure how we can. So the plots, okay, everything is hidden in there somewhere. Okay, so not sure. It's right here. So if I click add, okay, I just it's true. So with add, you know, you have all these different, you know, this is what the filters are, you know, you can do contours, you know, and then within under the contours, you can try different variables, you know. Let's try, I think in the notes, in the slides, we have I think we're good. Okay, yeah, thanks. So let's try Hardy Global, you know, which is another, yeah, then see, it's not doing anything until you hit apply. Okay, but, or draw. Oh, there's a draw button there. Yeah, next to the add. So it's not doing anything until you hit draw. Then, you know, you see something. Okay, so this is a really cool data set. But everything is fabricated. Everything is, you know, this data is just noise data, so that you show you all the different capability and functionality of Visit. So within this GUI, see, one of the cool things is if you don't like this bright background color, you can push of a button and then it turns black for you. So why is this here? I think for astrophysics simulation, you know, you're simulating the galaxy. The galaxy can't be white, so it has to be black. So that's why, maybe that's why. That's the thing that I can think of. See, and then all this title bar, you know, all this, those are controllable and can be changed. So it's really, yeah. You have a question, Barry?
I cannot see this window.
Oh, what screen?
No, I'm a computer. How can I see admins?
Is this, do we have this working on Google? What's it called?
Oh, this one, no.
No, it's,
That one's on the Hangout?
Yes.
no, the one on the left is on the
Oh, this one?
Is on the Hangout?
The one on the left.
This is on Hangout?
The demo, yeah, the demo.
Oh, okay. Okay.
So,
The slides.
There's a conversion that occurred when you hooked it up to the HDMI that changed the resolution, screen resolution. And it's really dependent on the monitor. So whatever the not the monitor, but the projector, whatever the projector screen resolution is, you may be able to change your display settings.
Well, I tried that. That's the max. Yeah.
So it doesn't auto convert.
Yeah.
I'm looking at it right now to see if I can figure out.
Okay,
a way to
okay.
get around that.
Okay. So that is how your screen should look like. Okay. So that's Visit. When you run Visit with higher resolution, that's what you will see. Okay.
Yeah, so is that.
So like I say, you know, the GUI part of the programming of the app application is definitely not their strong suit. See, they maybe should have a scroll bar here and detect that. But this is not what Visit is meant to do. Visit is meant to, you know, you can use Python scripting. Those are the most powerful capabilities. Okay, and the client server mode, which we will touch about. We will touch on this afternoon. Okay. So if you want to go through the steps, you know, these are very detailed steps, screenshots, you know, that will get you there, you know, and then you can change different properties, and every filters and every operation have the properties that you can change. You can limit the different numbers of, like this. You can change the different number of n, which means how many levels you want to see. That depends on your data. So you have to know a little bit about your data, the data ranges and all that, so that you can set the right range so that your visualization actually means something to you. Okay. All right. Same thing with pseudo-color and isosurfaces. These are just different filters. So do we want to go through those steps, or do we want to keep on going? You want to go through the steps? Okay, go ahead then. Ask me questions if you got stuck. I'll see if I can. Yeah, this, I don't know. No, there's no way to.
Go. If you don't do a mirror display, you might be able to do, instead of duplicate, extend it and see if that will work.
Yeah.
If you can extend it, or instead of mirroring, that might work.
Yeah, maybe I'll do that. I'll make it bigger here and drag it over.
But then you're losing that functionality of being able to see what you're displaying on the Google Hangout.
Oh, that's.
Google Hangout can see all this?
It's supposedly doing full screen, but I think it's just looking at this screen right now. Let me look at the Hangout and see.
Okay, good. Then we all can look at the Hangout then.
It's probably no way to there's no way to resize the window with this, I guess.
Showing you correct resolution, but
Trying to.
it's not displaying.
It's not displaying on Hangout at all?
It's showing on the Hangout.
Oh, the whole thing?
It's showing that, yeah, it's showing that on the Hangout right now, but it's not.
Okay.
It's not
They,
mirroring.
they all can get on the Hangout.
Correct.
Yeah.
If you want to do that.
Yeah, let's do that.
Okay.
Okay. You all can get on the Hangout if you like. How do we get on the Hangout?
Pull it up. The best way is just to go to portal.
Yeah, go to portal. Do you guys have the link?
Yeah, I can send them.
Yeah. Good then. Let me see if I can go through the pseudo color then. So and then you delete this, and then you add pseudo color and then Hardy Global. And then click draw. And then you should get a cube.
Once you get that done, bring it over to that screen.
Oh, okay. Yes, that resolution is still fixed. So if you do the pseudo color, you should see something like this. Oh, in your video?
Now you should be able to.
Okay. Okay, so,
Yeah.
all right, Martin.
Yeah, it seemed to be, I don't know if something was wrong with the interface.
Okay, then you can add in the slicing operator. So click on the operator. You get all these different. When you click on the operator, you get like analysis, debugging, geometry. So with some of the people, you can use Parallel and Visit for visualizations, but some people they also do analysis on that. So you can click on this, open different views, the spreadsheet views, look at your data, click on that, then you can see click on the visualization, and then your spreadsheet view data also get highlighted. With that, you can do analysis of that. You can do a 2D plot, you can do a histogram on your data. So actually, there's a lot you can do with this. Okay, so it really depends on what you want to do, and then just go for it. Okay. So with this, so slicing and then isosurface. Okay. See, with that, you slice everything away. So what you can do, okay, it's fine. That's fine. I'm good. Maybe you can help those people. Okay. So, yeah, see if they need help. So slicing of isosurfaces. Okay, hit draw and then click on the arrow to expand it, and then you can, under the percentage, you can do a 50%. Do a 50% and apply, you're gonna get something like this. So it's basically a data reduction, to to get you to see what you want to see, or you can
and why we do it in ways that might seem a little more painful than necessary. So I'm going to go in a little more depth than you might be expecting on not only how you do it, but also why we do it the way that we do it, if that doesn't alarm people too much. Just double check. Okay. We're sort of back, I think. Okay, so this is essentially what our big supercomputers look like. If you really abstract the heck out of them, it's a big room full of nodes, where each node sort of corresponds to what you think of as a computer, but they are interconnected in ways that allow them to communicate very, very fast. So that's what makes a supercomputer nowadays, is lots and lots of nodes that talk to each other real fast, that are grouped together in a computer room like across the way, and hidden behind a front-end node. So when you log in to one of our computers, Maverick or Stampede, what you're actually doing is you're logging into a front-end node here. And that's what you're actually doing. But when you start a big parallel job on the supercomputer, what you're doing is you're running it on a bunch of these nodes that are what we call compute nodes that are dedicated to you and which in a sense sit behind the front-end node. Okay? So that's the model I want you to think about when you think about our parallel systems, our large systems. Now, this model that I described earlier in the client-server model doesn't really work for us here at TACC, and here is why. For one thing, our compute nodes over here are not accessible to the outside network. You can't log in to our compute nodes from the internet, from any network connection. You can only log into them from this front-end node. So that means you can't have a network connection that connects a GUI process somewhere in the world to a compute node that's actually doing the work for you. You have to actually go through the front-end node in order to make that connection. So in fact, what happens is that we create a so-called tunnel that sits on the front-end node and basically takes data off the internet, bidirectionally off the internet, and hands it to its internal network. Okay, so there is essentially a little process that runs on the front-end node that is basically taking input from the GUI process and handing it to the server process, and then taking input from the server process and handing it to the GUI process. So that is problematic for us because we have very few of these front-end nodes, and that puts a burden on the front-end nodes, right? Those front-end nodes are now having to participate in the project. And since an arbitrary communication between a server and a client, we have no control over how much data that involves. We have no control over how much work this guy's having to do. And since we have a relatively few number of these front-end nodes, we can't have tunnels for arbitrary amounts of data going between the outside and the inside world all the time. So our systems people won't let us do it quite this way. So instead, there are a couple of alternatives that people out there in the real world expect us to be providing to them, and we don't. But I'm going to describe them to you so they fit into your mental model, and explain to you why we don't do it the way that a lot of people might expect. One way is by X forwarding. Now, are people typically Linux users or Windows users? I bet they're mostly Windows users, right? Well, we got a lot of Linux users. Okay, good. Linux applications use what we call an X server. The thing that is driving your display is called its X server. Now, if you want to do the same sort of stuff in Windows, you can run an X server on Windows, but Windows doesn't rely on it. You have an external guy, an external application that does the X server. But the long and the short is, what you can do is you can move the GUI process to another node like that, and then use X forwarding, and then connect that GUI process to the back end, and use the so-called X forwarding to make the output, the user interface from this process show up on your terminal, right? And now it looks like the application is running on your terminal, but in fact, it's running over here, right? Now that, of course, has the same problem the previous one does. Now you have a real process. It's not even a tunnel, it's a real heavyweight process that's running here on the front end node. And that, again, is very, very burdensome on that front end node, and our systems people say, won't work. Furthermore, this communication chat is very, very chatty, as we say it. There's a lot of signals go between a click you make in this window and the GUI process that actually is going to process that click. And a lot of times, that communication is actually a round trip. In other words, the message conveying that click goes over here and then has to come back in order to make the change in the user interface. So if you are in California and this guy's in New York, even in a world where we're communicating electronically and, speed of light, blah, 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 it's a quarter of a second to send a signal from New York to California. And if you do a round trip, that means every click is going to take you half a second to process. And believe me, that will be very, very painful. Maybe only 3,000 miles across the Earth, but the signal is actually going to go up against a satellite, right? And that's the way they haven't gone up there. So that's not a good solution for us. The big reason really being that we got this process here. So the next thing you might ask is, can we move that process from there back onto a compute node? I hope you appreciate the animation here. I spent a lot of time doing that animation. All right, so now we have moved the GUI process back here. And we could still really do X forwarding through the front end node and over here to the local system through a tunnel. And we'd be back to this. But let's get back to our earlier conversation that this connection here is chatty. And there's a lot of talking back and forth in order to be able to do that. But mind you, these are the ways that people in the Linux world expect remote applications to be run. You SSH into a system, you SSH it with a special character, -X or -Y, and its GUI will come back to your local service. And it's easy. Everybody expects to be able to do it that way. But this still doesn't do the job. We now have the GUI on a compute node, but it's still bad. We still do lots and lots of back and forth in order to communicate between the GUI and the application. So instead, we use an application called VNC. Show of hands, who's heard of VNC before? VNC is one of those unbelievable free lunches. I don't get why. It's a wonderful, wonderful thing. The idea of VNC is that you connect from a local system to a remote system. You start a so-called VNC server on the remote node. Then you start a client, a VNC client on your local node, and you connect them. Now you end up with a desktop that shows up on your display, but which is actually running on the remote display. And now they have gone to tremendous effort to optimize the transmission of information across this path, right? So now all of your mouse clicks and keystrokes go one way over here, and all that comes back are compressed pixels. So all your applications and everything are running over here, but the communication path is incredibly optimized. And this enables you, like I said earlier, to put up a desktop on your local system that actually is running on the remote system. And so if you run a job on this VNC desktop, you open up an Xterm window and you say GLX gears, that will actually be running here, and all that's going to come across the network here are compressed pixels onto your local display. So now what we can do is we can run a VNC server on a compute node. Actually, I was going to say this in the parallel version, but what you really do when you start a job on a parallel system is you use an interface called SBatch. And SBatch has two roles in life. One is to allocate a bunch of nodes of the supercomputer based on a scheduling algorithm and all sorts of stuff like that. And the other is to enable you to start jobs on those nodes that you've allocated. So what we're going to do is we're going to SBatch, instead of SBatching our application, SBatching ParaView or SBatching our simulation or something, we're going to SBatch VNC server. And that means that we now have VNC server over here, and we have a VNC client over here communicating by a tunnel, but transmitting a very controlled and manageable amount of data across the network. A data path that is completely optimized. It's heavily optimized by the VNC folk in order to minimize the burden through this tunnel. Okay, so this minimizes the work that our front end node has to do. It gives you a desktop that's actually running on a node that you've allocated and is essentially yours to do whatever you would, do whatever you want with. And this is the model that we use. So then you start up ParaView user interface, boom, it shows up here on your desktop. You start a ParaView, a parallel backend for ParaView, connect everything up, and you get ParaView running on your desk, but it appears to be running on your desk, but it in fact is running strictly on TACC resources, using potentially vast amounts of computing power. But it shows up here on your little laptop, and it is packaged. It's very neat for you to use. Now you might wonder, how complicated is it to set all that stuff up? And our old answer to that is, well, it really is a pain in the butt. But we have, in the past couple of years, built a specialized portal for doing this kind of work. And this is the easiest way to do visualization stuff using TACC resources. There is a special web page, viz.tacc.utexas.edu, that presents you with this interface. You can then log on to this user interface here using your TACC credentials. That brings you to this web page. You then specify whether you want Maverick or Stampede, other parameters of how you want your job to start up, and then hit go. The first time through, you'll have to set a VNC password, but the thing is, you'll hit this go button, and what that will do is it'll SBatch a bunch of stuff for you, so that now your job begins running on our supercomputing resources, and presents you with this web page. You type your VNC password in there, and lo and behold, now in your browser, you get your VNC desktop. Okay, so this is now a VNC desktop, and I'm going to go through this live if I possibly can. And anything that I run on this desktop now actually is running on the back end of one of our systems here. So let's see, just for grins, if I can make it actually happen. So I'm going to go to a new web page here, viz.tacc.utexas.edu, and boy, this really is low resolution. That is a pain in the butt. We need to get a better projector here. So I'm going to log in using my TACC credentials. I hope you all saw my password there. It's now authenticating. Just because it's a supercomputer does not mean it does anything fast. Okay, I want to start this job on Maverick. I have an allocation. I have services that I can bill to a project called ACC Viz. I want to use VNC. Here's my desktop size. I want to run one node, and I want to run 20 processes on that node, and I hit Start Job. It's SBatched that job. It is now queuing up that job, and if there is space available on the system, it will start the job for me. In the background here, you can see what is actually going on Maverick right now, and Maverick, there's not much going on Maverick at all, so this should start right up. So now Now we have Maverick. I can type in my VNC password. Now, this is a desktop right here that is actually running on Maverick. So if I do host name on it, it tells me I'm running on Maverick, maverick.tac.utexas.edu, and then this is the particular node name of the back-end compute node that I'm running this desktop on, right? Now from here, I can start visualization jobs. For example, using the document, if you look at our user guides, all of these steps is fully documented. I'm going to load some modules, which basically just adds particular tools to my tool chain. Python and ParaView. Module load, sorry. And now I can type a little special command, VGL run ParaView. And pretty soon now, we have ParaView running. Now, if this was my normal desktop, you'd have a reasonable, view of ParaView here. But here it is. So this is ParaView. It's running on a supercomputer across the hall, and everybody's happy and fine. And so I can now do anything I want to do in ParaView. I can animate stuff. I can do all the stuff that Ann showed you earlier. It will happen strictly on our systems. It will not burden your laptop at all. You will get performance. By the way, let me just demonstrate that. I can't even do that because I can't get enough of the menus up. Let's use a cylinder. There we are. Yeah, I know, but let's see, I can't even see my properties. Let's turn it off. Okay, this way we can do it. So here's properties, hit apply, and now if I could just see more of this window here. What a pain in the butt. Can't even close these things. You should see, there it is. It's off the screen, but there you have it. And you can see that I can interact with this guy. It's not going to be quite as fast as if this was actually happening on my local system, because it's having to transmit these frames from the remote system. But you can see that I can interact with it. It's doing all the rendering and stuff, and all that's happening on our end of things and producing the result here. Now, yes.
If I have a 5 gig like data file,
Then.
is it still on my laptop?
Yeah, no. The point is, I'm sorry, the point of all of this, and we'll get to this in the second session, is that you will have computed that data here. And so you don't want to ever bring that data to your local system. So one of the very fundamental reasons why we provide these remote visualization capabilities is because these data sets are computed here. They're too big to move home. And so even if you could do the visualization at home. And so this keeps the visualization proximate to where the data begins from, right? So now I'm going to show you another little magic trick about VNC. May I have a volunteer, please? Who has a VNC? Does anybody here have a VNC client on their laptop? You do? And we have a volunteer. Would you please try to connect your laptop, connect VNC to C221-704 at Maverick? 704. Okay, it's going to ask you for my password, which is GTV for me. G is in girl. 4 is in the number 4. And that references a old model of Alfa Romeo that happened really well. So you have that up and running?
It's still connecting. It's not that.
Yeah, it's being slow. 221.704.
It's writing dash. Not.
Yeah, that is the computer.
You need to connect like if you have a job.
All right, we're screwing up again. The magic here, excuse me, is that you can have your collaborators connect with the same VNC session. And if you do that, you're on the network, right?
Mm-hmm. Yeah, connected to another VNC session.
VNC service, C2.
Would that be a problem?
Yeah.
It is?
Yeah.
No.
I've done that before. But
No, you can do that. Anyway, the long and the short though is that you can have your collaborator in Cleveland be looking at your PowerView desktop while you're sitting in, say, San Diego. And she can put her cursor in this room, in this window here, and manipulate this stuff and press buttons and all of that stuff as if she was you, right? So this gives you a free collaborative environment that you can do VNC stuff in, that you can do visualization stuff in with your collaborators wherever they are and actually share a application as it's running, right? So those of you that have distributed groups, this is a wonderful, wonderful thing that you get for free by doing this VNC layer.
Can I ask you a question?
Yeah.
You just need to share your VNC password.
Yes, you need to share the VNC password. Another fact about VNC, it sends passwords in the clear. So never use a VNC password as anything that is, as something you need to keep secure. Okay, VNC passwords, that's why I just threw out my password. I don't care. It's not secure, and I never depend on it being secure. So this session will time out pretty soon, and it will lock up the screen, and I have to type in a real password to wake it up again. So long and short, don't depend on your VNC password, and share it widely and freely. All right. The last thing I want to demonstrate here, and I'm going to leave this up while I do it. I'm going to kill ParaView. And I'm going to now demonstrate something. There's a classic graphics application that runs on Linux, on X workstations called GLX Gears. And in this world, it doesn't work. So now I'm going to explain why that is and what you have to do about it. So here is our canonical, our natural VNC serving compute node. It's got this thing here called a VNC server. Mouse clicks and keystrokes come from outside and go to the server, and the pixels come out. And if you run an application on that server, on this node, that application will connect to the VNC server and to exchange all those mouse clicks just like they were coming from a real X server and communicate with the local desktop, ship pixels, and everything is fine and happy. And this is the model that VNC usually works in. But if you're trying to do fancy graphics, this model doesn't work. And the reason is because hardware graphics or graphics commands are different. And they go to a special library called your OpenGL library. Now, some versions of the VNC server have a software version of the OpenGL library that run inside the server. So now, all of your graphics commands, I want to show what this triangle looks like rotating. All of those commands go through this path to a software renderer in order to generate 3D pixels that go back to your desktop. Now, software rendering is way slow compared to hardware rendering, and each one of these nodes actually has a graphics card in it. So what we'd really like to do is be able to run those special 3D geometry and OpenGL instructions and send them to the OpenGL hardware rather than to a software version of OpenGL that's running inside the VNC server. And we do that by a wonderful little application called VGL Run. So now we can go back to ParaView, to our desktop. And instead of running GLX gears, which I'll demonstrate still doesn't work, I can run VGL Run GLX gears. And there it is. And in fact, it is running very fast. It doesn't appear to be running fast, but it's actually running here at 1800 frames per second. So it's running fast. It's running faster actually than the system here will actually display, right? Because it's only refreshing 60 times a second or something. But it's rendering very fast because it's using the hardware. And we are using this as a trick around the VNC server to provide high performance graphics across a VNC connection. So that's the model that we do any kind of visualization on our servers on. You start up a VNC session, then you can run any kind of graphics applications you want, as long as they're wrapped in this VGL Run wrapper. And if you do that, you get the power of a graphics card that is in our world, and the results come back to your desk. Okay, any other questions? Any questions I can answer about this? So if you want to run Visit, ParaView, ModFlow, any computer graphics application that we support, you run it this way. And this is our interface to doing remote visualization at TACC. Okay? Okay, so with that, let's take a break. Let's not hurry back because I think we're pretty well ahead of schedule here because Visit didn't take as long as we thought. So let's go ahead and take a break, and we'll answer questions, any questions you guys have, or people can go take a bio break or whatever, and we'll be back here at, say, 2:40, 2:50. Okay? Okay, anybody got any questions? Topics of interest, conversational points, alternative Alfa Romeos that they really, really liked? No? Okay, yes? Yes.
Can you go to the clarify the number of nodes, the number of API nodes in the way?
We're going to talk about that in parallel with later, because that's actually way more complicated than it has any reason to be. So let's talk about that. Other questions? Okay, have a nice break.
So you move lower.
Hang on just a second. Sorry?
That was the remote section?
I switched the remote to parallel.
Oh.
There's my old Alpha G. Well, I mean that's not mine, but that's the one. That is the coolest Alfa Romeo of all time.
How far?
Yeah. Italian car.
What's the top speed?
Well, not much. I'll tell you a funny thing about driving. The fun part comes on twisty roads between 30 and 50, and has nothing to do with the top speed of the car.
Just has to do how fast you can get from 30 to 50.
That's true.
And around the curve.
And around the curves. These S curves out here that we were discussing yesterday, they really are great. So yeah, I had a GTV for a long time, and a couple of other Alfa Romeos, but that was the good one. It is a beautiful little car.
How do you do the servicing?
There was a specialist. I was living in New York at the time, and there was a specialist who knew about Alfa Romeos. Yeah.
Over here?
Not that I know of here.
Yeah.
And that's why I haven't bought another one down here.
Oh.
They're very peculiar
Yeah.
to deal with. They have mechanical fuel injection, which is a cool thing. It is a little sort of shadow engine that sits right next to the real engine. It's synced together using a toothed belt. And it's like 4 little squirt guns. And at the appropriate time, each squirt gun squirts gas. It follows a metal tube into the cylinder. And so it's all completely mechanical. And it detects barometric pressure and temperature and all that and changes everything. You don't take it to your local mechanic and say,
Yeah.
it doesn't seem to be running right. They don't like that very much. Oh well, them's were the days. Okay.
So the WRF loader for Caravan, how do I get to that?
I did it for Greg Foss,
Yeah, that's
and it's a plugin that I built. I don't know how general it is because I really don't know that much about Wolf. I built the reader to read in that data, and so that's my my hesitation to make it public.
So that CDF stuff.
Yeah. But inside the concept of NetCDF, there's a lot of options. So So if you have an application for it, it would be a great place to start to build a specialized thing.
So
It does partitioning, it does all the important stuff.
So the paper you found is on hydrology.
Mhm.
I want to work with that guy.
Uh-huh.
But right now we need a more streamlined process to do that. Your Wolf reader allows me to get started.
Okay.
So this is what I want to pursue. He just recently got a lot of NSF grants on just doing the Wolf side, on the hydrology side.
Mhm.
But I haven't seen a lot on the visualization side. And he's in the EBSCO state.
Is where?
He's in the EBSCO state. And it's like EBSCO is, they have, since they are underrepresented in overall NSF, they create a special part of money just for the data. So you can access this special,
Mhm.
so easier to find.
Yeah, I'd be happy to give you that stuff. But I just want to make sure that if I do, that
Yes.
it's clear that it's not really.
Yeah, definitely.
It's a,
So,
sort of-
so the raw data that your reader can read,
Mhm.
can I have some of those too, just to show him
Yeah,
how
yeah.
it would be if he can get his data into Wolf, or if need to with the new proposal?
Well, actually, the only data sets that I have for Wolf are huge. And that was the real problem.
Is there like a single time steps?
There are single time steps, but even they are far huger. I mean, the whole purpose of that project was to try to run Wolf at extreme resolutions. So I don't know. We'd have to see if we can. I mean, I'd be happy to give you a huge one, but it is kind of dated.
Gigabytes?
Yeah, gigabytes.
Okay, then
Okay.
gigabytes, like 10 gigabytes?
I don't know.
One
I
step?
don't remember. But they're atypical of Wolf, I guess is all I'm really saying. And yeah, another piece of the magic is Wolf doesn't really give you the grid. Wolf gives you, you have to compute it with pressure. And so that's why I did it as a plugin, so that stuff could happen, so I could read in the grid compactly and expand it as part of the import. That's what I was doing.
So does it need a specific version of Parameter or 4.2?
I've built it for 4.2 and 4.1. It's not a lot of code, not really, so it's not really a big problem. And I built it externally to PowerView. So yeah, I can just give you a little piece of code.
Also, it is like you have the plugin for 4.1 too. I mean, as well.
I think we did. Now I don't really remember.
Yeah, I was
I get
discussing-
tangled up by grid
I was
stuff.
discussing with Carson, we wanted to use the data for benchmarking,
Uh-huh.
but he mentioned it would be a big thing for him to update all this stuff before too, so we better if we could just have the reader before one.
So this is for, so I'm reading
Yeah.
4.1 now.
I imagine it would just build for 4.1. I don't know any reason why it wouldn't just build
Okay.
for 4.1.
Again, for the reader point of view, it's easier to translate between 4.1 and 4.2
Okay,
because he has to deal with the rendering.
yeah.
But we do have to be sure, that we do try to at least pay lip service to keeping up with the latest versions of stuff. We
Yeah.
can't just do that.
Cool. So, yeah.
Actually, we're just sitting here. Let me show you what that is.
So can in the building of the code, do you use GCC or Intel compiler? ICC?
Either one.
Either one. Okay, good.
So Greg, we're still broadcasting this. This commentary is online.
Okay, anybody out there in the real world who'd like to see a little overview of a WRF data reader, you can now pay attention. WRF is the most common, I guess, it's the weather forecasting system that is used by NCAR, National Center for Atmospheric Research. And I believe everything you see on the 6 o'clock news comes from WRF, doesn't it? WRF, there it is.
Okay.
So, this is just, there's nothing fancy here. Okay, I wanted to see down here in the guts. See, it assumes that you have those pH things. It assumes that you want to create a wind variable from UV and W. And then, so it assumes you got latitude, longitude, pH, and PD. It assumes you want to do a WGS84 projection. Then it imports exactly the variables that are compiled in. That's why it's not really very general, right? Destaggers if it needs to. You know about stagger? Some of the variables in WRF are not cell-centered.
Oh.
They are face-centered. And so
face
you have to interpolate them back to the cell centers.
Oh, okay. Okay.
And then the cell centers become, then you offset the grid, so the cell centers become vertices and can do the dual of the grid. But, there's nothing terribly complicated in there. Here's where it puts the UV and W values into a wind vector and so forth. So there's a little glue here to make it show up right in the thing. But then there's just a CMake, it's that, and that creates a plugin. So
did you say you compile it outside of the ParaView?
yeah,
Okay, so
yeah.
So you just do a CMake?
Huh?
Then how come when I compile the plugin that Carson wrote?
Don't get me started.
It's different.
Greg, can you run the Viz Pro? Can you access Stampede as well?
Yes, yes.
Okay. So yeah, so we
Blah, blah, blah. I didn't find ParaView, so.
access. So this project right here is
Shit. Yes, it needs some other
GDAL.
libraries that are not there,
Yeah.
but that's
Yeah.
another GDAL, whatever that guy is. That's what does the projection from latitude and longitude to WGS space. But yeah, so it really is that simple.
Okay.
So
Cool.
why do other plugins not work that way?
Then the binary it creates, how do I point it to the?
You put it in a directory in your, then if nothing else at all, if you start a ParaView, you go up here to Tools, Manage Plugins,
And you can import it in.
and then you can import
specify
yeah.
where it is.
Yeah,
Okay.
but if you put it in a magic place, it will find it for you.
Yeah, yeah. Where is that magic place?
Different on every system. Apparently, but it's telling us right here. It's where they're automatically searched for.
Oh, okay. Yeah, if I drop it in there.
I think too, like, cause with the Osprey, like person, if you use his module file, somehow he specified there that it was automatically loaded if you use his module file. I don't know if there's something
He builds it as a real ParaView plugin.
Yeah.
He builds it in the ParaView.
In the
system.
ParaView
okay,
itself.
okay. So this is different. This
This,
is like
yeah, because frankly, whenever I write a bug in here and I want to fix it, I don't want to read the paragraph.
yeah.
Just imagine how long it's going to take. Then I found out, it means Intel compiler which is not accessible from the VSLab. And then all the module and stamping I can use in the VSLab.
Yeah.
Yeah.
To do everything
So,
from
so
scratch.
this is easy. We just get those libraries in there. Just work fine.
In Visit is more this way. If you write a plugin for a data loader plugin for Visit, you can also compile it offline and you just
Yeah.
Yeah, of course you can. That's the whole
Plugin concept.
the whole concept of plugin.
Yeah, you don't to
Yeah,
compile
so-
the whole binary of the whole.
Yeah, I had that. Like, Visit, I was trying to use a reader that Dave had written a while ago for Enzo data, but it was like a different, just slightly different because it included ghost zones. I couldn't get Visit to recognize the other one, so I ended up just recompiling the whole thing. But
Yeah, one of the first things I was going to do for that when I really got roped into that Intel thing was make the Manta plugin or the Osprey plugin external, just because I was having to fix it.
right.
Then
Ran out of time.
when you're successful in everything for that.
Well, I wasn't advocating for it. I was just doing it, but I ran out of time, so they didn't finish.
I just wanted to ask you about, because you mentioned that if you have another, for example, non-compatible files, you would be able to make that compatible to and it just depends on how you should do that.
It depends. What does your data look like currently?
Okay, it is like formatting.
Yeah.
Okay, it might be ASCII or
Was it like, is it a grid of data or?
Points in space with connectivity.
yes, let's say that.
Okay, well, I think in most cases, your easiest bet is to do one of the BTK formats. So there's like BTK. I'll show you the website, but it's probably
What do we get another text?
probably the easiest.
Pardon me?
What do we get
Oh,
another
this is
text?
nice.
Where do we get our text data?
How come this is the second text data?
Oh. Well, I mean, people with not a lot of data.
So what is your comment on ParaView and InFocus?
Well, ParaView doesn't lend itself to InfoBase.
Yeah.
So they have a separate kitware application. At least they used to. I think they might have.
Maybe they
Withdrawn.
integrate into VTK.
Yeah,
You found it.
yeah, I did. It was hiding right here. I don't think they got really far on it. I'm not really sure I'd really recommend it. I mean, people like Spotify, not Spotify, Spotfire, and there's some commercial products out there that are so much better than anything that
With InFocus.
InfoBase is silly. And the reason is because there's just a shitload of money.
Oh, yeah.
And there was a shitload of money in visualization inside this. I think our tools would be better.
Yeah.
So how do I get to that plugin?
I'll send it to you.
Same thing.
Yeah. I'll figure out what the libraries are for it.
It's just.
Did you turn off the
If
screen
there wasn't
share?
any of that, we would probably-
I don't think so.
So, yeah.
So if I go here,
You've got on another window, it does
Another
its own
one?
little pop out. Do like a command up or something.
Command up.
Yeah, command up there. Control.
Well, actually, that one's more like mine. I had one of those too.
Oh, it's none of those around.
Wonderful car until it's no longer wonderful, and that's a piece of shit.
And then it's like.
So I need to
times
find
I have
that.
to take it to the shop. Yeah, it's on another Google Chrome window.
But I don't have any other Chrome windows. Oh, I'm sorry. It's probably another tab.
Oh, I don't think it'll be a tab per se. Oh. Yeah, here you go.
So. So doing PowerPoint. Yep. At some point, is that direct connect issue. Still doing the same thing. Is it not working?
Now it's showing what's on your mouse.
Sorry?
We had it where it was showing this on your screen, and then it was showing that on the Hangout.
Can we, let's just swap them. Can't we just swap them? Swap displays.
And then see what happens.
Yeah. Yeah. Good. That's perfect. That'll be fun. All right. Let's get back to it here. Get this over with before the so we can have our hands-on session and still get out of here before the thunderstorm starts. Yeah. That's not good.
No, that's not what we want.
No.
Exit show. Let's look at your display settings.
I did shift it.
So we can do an arrangement change, I think. We did a mirror. We didn't change that.
We did change that. So try going to the best for external display. So I think it's probably where we were before.
And then we have
Okay,
not that.
but then the question is what's over there.
Yeah.
Good? Okay. Let's get on then to parallel visualization at TACC. So far, we've showed you, we've given you an overview of visualization as a whole. We have showed you how to use Visit and ParaView. We've talked a little bit about how you use our facilities. And now I want to spend a little while talking about supercomputing level visualization. Why you would really want to come to TACC and use our biggest systems for doing visualization. The picture you're looking at here is a data set that we have. I believe it's actually that turbulent flow data set, isosurface. And each one of these areas of color you see here is a piece of the overall data that's being generated on a separate node. So looking at this, you can get an idea of how large this computation is. By the fact, it's reusing 8 colors over and over and over again for these partitions. So this gives you an idea of how many partitions there are along each side. Cubed would give you the total number of processes that are being used to do this picture. And this is a close-up view of some of it, so you can see how finely detailed the data is. So if we look at the visualization problems that we deal with, we can think of them as being sort of a pyramid in scope. At the bottom of the pyramid is the largest bulk of the visualization problems that people actually do. The data is relatively small. Your office machine or your laptop is perfectly fine for doing the visualization. And the fact is that really is the bulk of the side viz work that's actually being done. From my point of view, not necessarily the most interesting part. One step up the ladder, we start getting to medium scale problems where it's starting to get pretty painful to move the data set around from place to place. And the requirements for doing visualization, for running PowerView and Visit, move away from what you can normally do on a 32 gig laptop, and you start needing serious amounts of memory, in the hundreds of gigabytes, more compute power, maybe a more powerful GPU, in order to be able to provide the kind of performance that you really need to do interactive visualization of this stuff. Higher up the ladder, we start getting into data sets that you really can't move from site to site because they're just on the order of many gigabytes or terabytes in size. And you can move them, but it takes many minutes or hours to move the data set. And even once you get it to your local machine, you're not going to be able to do it on any simple office scale machine that you might have at your local site. And at the very tip of the pyramid are some problems that really these days are only showing up at the national labs and a few other places, where the problem sizes are so large that you literally can't afford to write the data out from the memory of the supercomputer where it's being computed to its own storage systems. Just doing that is going to take more time away from your computation than your computation itself is going to take. The fact of the matter is computers are really fast and I/O is really slow. And that is nowhere becoming more apparent in this stuff. So moving on back down to the bottom of the pyramid, for these medium and small scale problems, knock yourself out. Bring your data local, use your own systems. You don't really need us, but we can probably help with, you can probably get better performance if you do use our stuff, and we can give you expertise and stuff like that, but you really don't have major problems. But higher up the pyramid, you start getting to problems that are too large for any one system to compute. And that's really where our bread and butter is. That's why we have visualization supercomputers across the hall, is for a pretty wide range of problems that people who do supercomputing computational science really do create. And of course, at the very tip of the pyramid are those huge problems. And we do occasionally do what we call in situ or co-processing visualization, where we can address those problems as well. We're actually working on a project with the DOE right now, which is focusing on this class of problems. And we can help that, but that starts getting to be really specialized stuff. So let's start thinking about what parallel systems really are and how we use them. From the outside world, you really, when you log into Maverick or Stampede, it's really just a box you SSH into and do your work. And so it's kind of a black box, or in this case, a green box. But that's not really, but it's important to know actually what happens inside that green box. So I'm going to do a very quick overview of what parallel systems are now,
so that we can talk later on about what is involved in doing visualization on it. So the classic kind of parallel system that we have nowadays is what we call distributed memory parallel systems. Distributed memory parallel systems are essentially a room full of what you normally think of as pretty powerful computers, but which are effectively really standalone computers that are connected by a high-speed internal network. And by this, I'm talking about 500 megabytes a second to a gigabyte a second in communication time from any node to any other node without getting in each other's way. So this is vastly faster than what you normally expect, on the network that you have that connects your computer to the wall. This is we call it. This is an InfiniBand network for all of our systems here. There are a couple of other products like it, but it's basically a very, very, very fast network. Connected to that network also is a parallel access file system. So this allows you to create files that are equally accessible by any node that are on the system. And furthermore, lots of these nodes can hit the same file in this parallel file system simultaneously, right? So you can create files that are accessible to any of these nodes and be able to read in parts of the file simultaneously on different nodes. So this is your mental model, again, of a large distributed system, distributed parallel system. And in this world, this actually the trick of using these systems is to get lots and lots of different nodes to share the overall job that you have, right? And if you think about the problem of baking a pie, doubling the number of ovens you have will not make baking that pie faster, right? So there's some technique, you have to use some technique of parallelizing the job so that these different nodes, think of them as different ovens, can each work on a different part of the data without interfering with one another, but where the sum total of the work they do is the job that you actually want done, okay? I like the oven and pie analogy better than the old one I used to use, which was women and pregnancies. So that said, okay, so in this world, these guys communicate by what we call message passing, okay? So in this world, any node can send a message to any other node that is essentially just a bunch of bytes. And what the interface, it's called MPI, the message passing interface, does is it basically just says, I'm node 12 and I'm sending 32 bytes to node 36. And it's going to expect that node 36 knows what to do with them, right? So that's how they communicate. They do explicit message passing. Any node can send a message to any other node that's expecting it, and send them and communicate with them. So MPI, message passing interface, is the model that we use for these distributed systems, and it's a tool that if you want to do parallel programming, you need to understand nowadays. Now, looking a little closer at each one of those nodes, they themselves are parallel computers, and the machines you have sitting in front of you on your desks are also parallel computers, because at least I imagine almost all of them are multi-core. Now, a multi-core computer is essentially a computer that has a bunch of what we used to think of as CPUs. And those CPUs are all really independent computers that are able to access one shared memory system. Okay? So they have different caching techniques. If you know anything about caching, it sort of looks like that. But the long and the short is, it's like having a bunch of different CPUs in the same box sharing the same memory. And so communication between them amounts to identifying a location in system memory. Then any one of those computers, any one of those cores, can write into that location in memory, and any other core can then read that location in memory, right? And this is much faster. It's faster because it's communicating strictly within the node. Doesn't involve anything that you normally think of as a network. Internally, it is kind of a network, but everything happens by one guy storing something into a memory location and another guy reading it back. And now, in order to make that work, you need to think about synchronization. If I am the node that is expecting to read that value back, I got to know that the other guy wrote it
and is finished with it in order to read back something that is valid, right? So it involves synchronization. Each one of these guys has got to be able to lock out everybody else from accessing that memory location. Then he writes it and then unlocks it so somebody else can grab it. And that's what we call synchronization, locking. There's a lot of terms for it, semaphores. And that actually is a reasonably expensive operation at a compute level. So in order to do these things, oh, I'm sorry, one other thing. You can also run MPI on these guys, and they can communicate by message passing. And since they don't involve a network, it is somewhat faster, but it again is that explicit sending messages from place to place. But back to our original guy here. In order to have a single job that is parallelized on your laptop, you need to get multiple cores working on it. I mean, that's what it means to run in parallel. And that involves making applications what we call thread safe. So that threads, which are individual programs running on these cores, can share this memory without stepping on each other. Okay, an additional form of parallelism is so-called accelerated systems or offload systems. Offload systems are systems where we've put a specialized accelerator in each one of those nodes, right? And the standard accelerator that everybody's familiar with are graphics cards. Your laptop, it may not actually have an explicit graphics card, but it has a piece of silicon in it that is dedicated to the job of doing graphics. Turns out that same silicon can be used for doing computation. And so it's a hot topic in the industry right now to use GPU accelerators, graphical processing unit accelerators, to do real science. And so if you look at a system like Maverick, it has a lot of GPUs in it, 132 of them. And a lot of the use of Maverick are people that want to do compute jobs, that want to take advantage of those GPUs, not for doing graphics, but for doing very fast processing. And so it amounts to an accelerator GPU with its own memory. And if we want to use it, what we do is we take a block of memory from system memory, a block of data from system memory. We move it into the accelerator memory. Notice again the cute animations. The accelerator then is able to work on it, creating a result, which we then copy back to the system memory, right? But none of these cores can directly address this memory, and this guy can't directly address that memory. So in order to take advantage of accelerators like this, what you have to do is explicitly move a block of data to the accelerator where it's going to be computed on, and then bring the results back, right? So that's it. You can have an enormous number of cores in here, and they can work really, really, really fast. But you got that basic problem of moving the data in and out in order to be able to take advantage of it. Now, I also want to say here, there is another form of accelerator now that is on Stampede. Every node of Stampede has what we call an Intel Xeon Phi accelerator, which is a specialized accelerator. It's not a GPU, but it sort of fills the same role. So when you hear people talking about accelerating applications on Stampede with the Xeon Phi, it's directly analogous to using a GPU for doing accelerated compute on the Stampede nodes. And of course now you can combine these things together. So what you're seeing here is a bunch of nodes, each one of which is multi-core and has accelerators that are interconnected on a high-speed network and have access to a parallel file system. So from 50,000 feet, this is what Stampede looks like. Every one of 64,000 nodes, 6,400 nodes at Stampede, is an accelerated multi-core, powerful, standalone computer that is connected to every other node in the system by a high-speed internal network, and it has a parallel file system. So now, why would we want to use these things? Why would we want to go parallel and use these computers, these big systems, for doing our job? Well, there are three resources in this thing to point at. The first is the compute. Right there, you're seeing, let's do that again, it's showing you the compute resources of this thing. And by using more than one node here, we can use more than the number of cores that are accessible on one node. And we can use more than one accelerator. And we can bring more compute to the problem than you can ever do on a single node, right? The second resource is the system memory. By using multiple nodes here, we provide our application with a lot more memory, a lot more real, physical, good old-fashioned memory than any single node can have. On Maverick, each one of these nodes has 1/4 of a terabyte of real memory. So if you start doing parallel compute on them, you get real memory that is not disk memory, but real memory that can be in the order of tens and 20s of terabytes. So serious amounts of memory. The third thing to point out here are the data paths. In the visualization world, what you're going to end up with, generally speaking, is big data sets that are sitting down here in a parallel file system. And the single most expensive operation you're going to do to those data sets is the process of reading it in, just loading it from a parallel file system into your system memory, right? And each one of these nodes here has a pipe to the high-speed network that is much, much thinner than the overall pipe to the parallel access file system, right? So by using a bunch of different nodes, you can use a bunch of pipes simultaneously, and you can get a much higher bandwidth out of your file system and into your compute process. And in different cases, each one of these three is the goal of running parallel. Sometimes you're going to want to go parallel because you don't have enough compute. Other times you're going to want to go parallel because you don't have enough memory. And other times because it's taking too damn long to read your data in. And all three of them are valid reasons for going parallel. The reality is often they're all true simultaneously. But I want you to think of those three things as being the resources that you're really gaining by going parallel on these things. So just quickly looking at the systems that we have here available, we have Maverick. It's about a 2-year-old system now. It's basically an HP system, but largely designed by us. Each one of the nodes, each one of 132 nodes, is a 20-core Ivy Bridge node. So this is like one generation back of the latest and greatest Intel stuff now. But it's got 20 cores in it. I bet there's not a laptop in here that has more than 4. Each one of the nodes has 1/4 terabyte of memory. It has a high-powered NVIDIA GPU, a very, very high-speed interconnect, and it is designed really to provide interactive visualization of absurdly large data sets. But the big machine you see across the hall is Stampede. Stampede is, I guess it's also about 2 years old. It's been as high as the 5th largest open science computers in the world. It is over 6,400 general purpose computers interconnected by, again, a very, very high speed interconnect. Each one has a mere 16 cores and 32 gigabytes of RAM, but it has these Xeon Phi co-processors. And the aggregate of that is a huge amount of compute. 16 of its nodes are also large memory nodes. So there you have twice as many cores and a huge chunk of memory, a terabyte of memory inside that box. And then there are 128 so-called GPU or Viz nodes that are the same as other compute nodes, but they also have a pretty powerful GPU. So that's what our visualization supercomputers really look like, okay? And if we take a step back, all these computers are interconnected at TACC. And so you do want to think about the overall system architecture, which is this. All of our systems here are connected by sharing one gigantic file system called Stockyard. All of our systems here have corny Texas names, not responsive. But we have this huge file system called Stockyard, and it's a parallel file system, and it is accessible from Maverick and from Stampede. Simultaneously, each one of them has a private home file system where your normal files would be. And Stampede has a very large scratch file system where you can put sort of temporary files. But this is the model that I want you to think about, because the beauty of this is it doesn't matter which one of these nodes generates data that you want to visualize, because that data is all going to be down here in a shared file system. And so you can always do the compute on the appropriate compute resource and use the appropriate resource at the appropriate time. Does that make sense to people? Okay. So now running parallel processes, I gave a little lecture about this in the earlier part. I guess I didn't really separate these two talks very well. But essentially what you do when you run a parallel process on Stampede or Maverick is that you SSH, secure shell, into our front end node. And that essentially gives you a command line on our front end node. From that command line, you can S-batch a job. And the role of S-batching a job is first to allocate a bunch of nodes of the system. And second, to start jobs running on those nodes. Okay, so the typical way you start a huge simulation at TACC is that you write a little S-batch job script. And that job script is going to describe what nodes you want, how you want to run them, and what jobs you want to run on. And this magic program called IB Run enables you actually to start a job simultaneously in all the different nodes. You know, so typically the way a simulation runs is you're running exactly the same code on each one of the nodes, but each one's responsible for a different part of the data. So the only thing they really know about themselves is which one they are. And so all of these guys are running exactly the same, but this guy knows he's 0, that guy knows he's 1, and so forth. And they know how to do the right thing from there. So now the question is, what do visualization softwares look like on this thing? And the good news is both ParaView and Visit have been engineered to run in parallel, and they look exactly the same running in parallel as they do when they're running on your local desktop. So the beauty of that is you'll get no more confused by this by running it on Maverick and Stampede than you would if you're running it on your local desktop. Doesn't help with the degree to which you're confused to begin with, but it doesn't make it any worse. And they depend on a client-server architecture, like I described earlier. And the idea is you allocate a bunch of nodes for the server processes. You run a client locally, and you connect them to then you run the server processes on all your server nodes under MPI and connect everything up, and lo and behold, you've got a beautiful job. Unfortunately, neither ParaView nor Visit are multi-threaded. That means that if you go back to one of those earlier pictures we had where there were a bunch of cores in each node, ParaView and Visit cannot take advantage of all of those nodes in a single process. The processes are not thread safe. So because of that, you have one of two choices. Either you can run one process on that node that uses one core, or you can run 20 processes on that node, each one of which has one core. And in doing that, you use all 20 of the cores, right? The downside of that is each one of them is only going to have 1/20th of the memory, and you're going to have a lot more internal communication. So this is what you asked earlier about wayness. Wayness is when you start up your jobs, you're going to tell it not only how many nodes you want, but you're going to tell it how many processes you want. And if you divide the number of processes you ask for by the number of nodes you ask for, you get the wayness. How many way is my program running on each node? Is it running 1-way, 4-way, 20-way, right? So that's the notion you need to think of in terms of wayness. It's how many individual processes are going to be run on each node. The upside being you can use more cores. The downside being it'll involve more overhead in order to use it. So there's no good answer about when you want to do it one way and when you want to do it the other way. Naively, we assume you always want to go as many ways as you can, but generally speaking, keep that in mind because it can trip you up pretty good. So now if we do the client-server visualization, I have no idea where this is going. Let me add it. So this runs right like I described earlier. We allocate a node set. We start our back-end server processes. Because this is Power Viewer Visit that we're modeling, we actually start a bunch on each node, not intentionally looking like Mickey Mouse. One of those is magic. It is the so-called root node, or node number 0, and it provides the communication to an outside client process. Connect them up, and you've got a parallel visualization application running. Does that make sense to people? That's how we do it. Where this is all happening, using VNC and stuff like that. Yeah. Yes. Yeah. So now you might wonder how you actually break up the pie so that 20 ovens can cook it at the same time. That analogy now is completely broken down. But the idea is, in high performance computing, is what we call data parallel application, data parallel algorithms. You basically take the domain that you want to compute on, you divide it up into subdomains, assign one of those subdomains to each process, and have those subdomains computed in parallel. Then periodically, you reconcile what happens at the boundaries between the partitions, and you get the right answer for the overall data space. So let's suppose we have a two-dimensional domain here. In order to run parallel on this four-way, we're going to chop this domain up into 4 partitions. And we're going to assign one of these partitions to each one of the nodes, each one of the 4 processes we're going to be using to do this visualization. Now, because we want to get the right answers along this boundary right here, we maintain something called ghost zones. And ghost zones are essentially cells that are borrowed from our neighbor. So these cells here are copied here. And that means if I want to compute what's happening right there on the face of my partition, the data, all the data that may be pertinent to it is available. Does that make sense to people? So that means, for example, if I have a curved surface that goes from here through here, and I'm computing the surface normal by looking at the gradient in this region, I have all of the gradient in the vicinity, all the data in the vicinity to compute that gradient from. If I didn't do that, I'd have only these 2 cells to compute the gradient at this point, and only these 2 cells to compute the gradient at that point, but that point is actually the same as this point. And so I get a different answer for the 2 partitions. And you will see a seam in smooth surfaces that derive from exactly this problem. So these systems always have to maintain ghost zones. And essentially, you create these partitions with ghost zones, you compute as if the ghost zones aren't there, then you throw away any data product you have that happens, that is created in those ghost zones, and you get the right answer for the real zones. Now, sometimes these data parallel algorithms work really, really well, because a lot of the algorithms that we perform on are very local. One such algorithm is isocontours. Two-dimensional isocontours, we discussed this earlier, my mind is really going here at the end of the day, are two-dimensional isosurfaces, or contour lines. Thank you. God. I can compute contour lines in each one of these guys completely independently, right? So there's a contour line, and it's being computed. If you stitch this together, you get a continuous line here. But I can compute the results in each one of these partitions completely independently, given that I have these ghost zones to make sure that I get the right answer at the faces. So it's a beautiful thing, right? Well, sometimes it doesn't work so well. If most of your isosurface action is in one partition, that guy is going to do all the work. There's no load balancing that's going on here. This guy is generating all the isocontour that lies in its memory. Whereas this guy is only generating a little bit of isocontour. He's going to be done, you know, in early February, whereas this guy is going to still be working in November. So data parallel algorithms are not perfect, but they give you a good place to start for a lot of algorithms. But then I just want to leave you with this notion. There are some algorithms that don't work well at all. The most important being a streamline. I'm not sure we really talked much about streamlines earlier, but imagine that we're trying to model the flow from the air conditioning system in this room. I could imagine there being a data set that describes at every point in this room what direction the wind is blowing. And then I could imagine dropping a soap bubble at the vent here. And I could watch how that soap bubble is being carried around by the wind that I know to be existing in the room. And I can compute that. It's called a streamline. The problem is that computing a streamline is an inherently serial process. If I seed my streamline at this point and start tracing the streamline, it's going to truck around for a while there on processor 0. Then it's going to truck around on processor 2 or 1. It's going to go back and play around in processor 0 for a little while. And at no time in this process did anything ever happen in parallel, right? So there are going to be some algorithms that you're going to run into that are inherently serial algorithms. And so no matter how much compute you throw at computing that streamline, it is not going to go one bit faster than it would on one node. Now I say that with one big caveat. One is I could have seeded this whole data set with a whole bunch of streamlines. And I could compute each one of those streamlines in parallel. And they'd all be trading off the streamlines they're currently working on as these particles go from partition to partition. And you could get a great deal of parallelism there, and that's a good thing. The other thing is that I could hold the whole vector field in memory here, right? This vector field might have been too large to hold on one node. So in order to compute this streamline on one node, I might have been able to trace it here until it exited the part that I have in memory. But then I'm going to go out and have to get the other part from disk. And that's going to be way slow, right? So here, this algorithm is accelerated not by the amount of compute that you have available, but by the aggregate amount of memory that all of the nodes bring and enable you to spread your data out on. Does that make sense to people? I just want to say a little bit about parallel rendering. The product of doing these data parallel algorithms is you end up with stuff to render on all the nodes. And so you could run one of these things, 1024 away on Maverick, and you end up with part of what you want to be looking at on every one of those 1024 nodes. And lo and behold, you've got one screen you want to put the picture on. And that means we have to use techniques for doing parallel rendering. How you generate a single picture of data that is spread out over a bunch of different machines. And there are various ways of doing that. It's a hot topic of research. We're doing a lot of it here at TACC. But the two simplest are, you can either render all of the geometry on this guy on this node, and all of the geometry on that guy on that node, and then composite them together, and that would work. Or you could gather all this geometry onto one node and generate it all in one place. But those are really your two alternatives. One is to render the data where it is and composite it, which takes a lot of communication time. The other is to gather all that data to one place and render it, which may run a lot faster, but requires you to move all that data. So there are all sorts of trade-offs, once again, in how to do this. PowerView and Visit both support both techniques of doing it, and they have defaults. They'll try to be smart, but they won't always be smart. And so it's something you need to remember. Now, the next thing I want to talk about is data formats. The reason for this is because in order for these things to run fast, the data that you want your nodes to be working on has got to be local to that node, right? In other words, if I got 1024 nodes that are available to run, I need to have 1/1024th of the data on each one of those nodes in order to take advantage of it. Most obvious thing in the world, right? But if I can't have each one of them access its part of the data simultaneously, then I have to read in all of that data into one node, figure out how to chop it up, and then spread it out. And so I've lost any advantage of parallel I/O. All of that data has to be read into one node, and then, actually there are two ways of going about this, I'll get into in a moment. All of the data has to be brought to one node, partitioned, and distributed. Or all of the data is brought into all of the nodes, and parts are thrown away. You got either one, but they're both disastrous. So what we do instead is we have so-called parallel data formats, ways to put data onto the disk in a manner in which individual nodes can figure out what part they're going to be responsible for and read in their part of the data while everybody else is reading in their part of the data. That way now you have 1,024 nodes working on this big data set. Each one of them is only accessing 1/1024th of the data. And I/O goes a lot faster than one node reading in all of it. But in order for that to happen, each node has to be able to look at this data set and decide what part of the data set it's responsible for, right? So, not all formats support that. If you have, once again, my model of this room, but we're just doing it as a tetrahedral soup. If I've just listed out a huge number of vertices and a huge number of tetrahedra, there's no way to look at it and say, I want the part that goes from here to here. Right? You could pull out arbitrary parts. You can't pull out nice, compact pieces that you can compute on. So we call that a data soup architecture, and it's a really bad thing for doing parallel compute. Fortunately, there are alternatives that work out really, really well. Any structured data format, by structured I mean you can describe the connectivity of the data algorithmically instead of explicitly, can be partitioned into parallel. If this data here is 1,024 that way, 1,024 that way, and 256 this way, and we've divided it into two pieces, I can figure out what part of that data set is mine, and Terry can figure out what part of that data set is hers. And we can each read it in parallel, assuming that the hardware supports parallel I/O, right? So that's what we call a structured data format. And a lot of structured data formats, there are a lot of readers in both ParaView and Visit that read in structured data formats and support this sort of automatic partitioning of the data into however many pieces it needs to be. And it's a wonderful thing. Again, unstructured data doesn't work real well. And then there are also so-called parallel formats, specifically parallel formats, where the data on the disk is represented as explicitly parallelized. You could imagine that I break up the data set that describes this room into 1,024 discrete files, whereas each file contains one nice little chunk of the data that is in this room, right? That way everybody just reads in its file and everybody's happy. And that works out pretty well with one exception. There are 1,024 files in a directory somewhere. And if you've ever used one of our supercomputers, you will know that unless you're real careful, if you go into a directory that's got a lot of files and you type ls to find out what's in that directory, it will go away for a long time, right? Because we have a so-called metadata server that involves these shared file systems. So having huge number of files is not necessarily a good thing. So there are other formats that allow you to do this sort of explicit partitioning, but within a limited number of files. And that, we heard earlier discussions of the Exodus format. There's also NetCDF and HDF5 formats that do support having essentially multiple logical files inside one real file. Now, the other thing I want to say about this is the source of the data that you're working on here is very often a parallel process itself. You may be looking at a visualization of a simulation that was performed on Stampede in the first place, which means that at some point that computation was already parallelized in order for Stampede to use it. So often that data gets gathered back together into a single gigantic data set and becomes tetrahedral soup. But if you can modify the application to preserve the partition that's already got in a partitioned format for output, you're way ahead of the game. And so that's a bit of high performance computing magic, is to preserve that partitioning to whatever extent you possibly can. I guess this slide pretty much says the same as that last slide. There are a bunch of different native formats in ParaView that do support one file per partition, and that's their drawback. Silo formats, NetCDF and HDF, all support multiple partitions in a single file. And there are a bunch, there's as many data formats out there as there are graduate students. And because of that, some of them are well supported and do beautiful stuff. Those are the ones that are at the national labs primarily. And others are problems. So I would encourage you to do a little study of what data structures there are out there before you write simulations or anything. You're going to write huge data sets, because it really does make sense to be smart about how you write your data, because you're going to be reading it back in. All right, so that's all I wanted to say about parallel data formats. I now want to say something about sort of the model that we use when we do visualization. And this is the straightforward, simple, common way of doing post-process visualization, and this is the bread and butter. You run a simulation on some supercomputer somewhere, and every so often it will dump its guts, the state of all of its variables, into storage. And so you will essentially put time steps of data into the storage system, and then the simulation will finish. Now, sometime later, you will then start a visualization program on some other node, some other host, possibly, maybe the same one, who knows. And you'll be reading that data back in, time step after time step. And so you will have paid a huge price to write all that data out and read all that data back in. So instead of doing post-processing, I guess I also wanted to say, this is one of the beauties of Stockyard, that we can run the simulation on Stampede, dump the output into our common shared file system, and then read it in from the common shared file system to whichever other of the machines we want to use for doing the visualization. And this is why I really wanted to show that slide earlier about our overall TACC architecture. That by using this common file system, we can always use the machine that is appropriate for the computation and really simplify the problem of moving data from machine to machine. Now, with these huge data sets, the fundamental problem is that they're huge. And because they're huge, writing them is horribly expensive. And so the big hot topic in a lot of the stuff that I work on these days is figuring out how to visualize data as it's being computed, rather than in this post-processing world where we've written this data out and read it back in. The reason being, as you're computing it, it's sitting there in main memory, right? And you can visualize it without doing any I/O. It's right there for you. And so we talk about doing visualization nowadays as possibly co-processing, creating two different partitions of your overall system and letting this one do visualization on this one's data and communicating using that super high-speed internal network. Or in situ processing. That is to incorporate the visualization directly in the simulation itself. So if you like, here is one of these nodes that is doing a simulation, and part of that simulation is actually going to be code that is doing visualization as the simulation is running, right? And it's beautiful because you don't have to write this damn data set out to disk, which is incredibly, well, relatively speaking, very, very slow. Now, there are problems with this. In order to make this work, you pretty much have to know what you're going to be looking for when you set this all up, because you can't turn the clock back. Because you specify a camera position and say, I want to visualize this data from this particular point of view, and every time you generate a new time step, you take that picture of it, right? But then if you decide later on you really wanted to be looking at it from over here, the data is gone. The data has already been thrown away, and the simulation has moved ahead in time, right? So in order for this to work, you really have to have a pretty good idea of what you're going to want to look for in your data, so that your in situ visualization, which is not interactive and not exploratory, so that you get out of it what you really want, what you really need to get out of it. Make sense to people? This is really, like I said, the bleeding edge of visualization these days. Co-processing and in situ processing is available using ParaView and Visit. It is not a graceful thing, and both ParaView and Visit can do it, but it's hard. It is not an easy thing to do. We can help you with that if you really want to do it. The other thing I wanted to mention is some stuff we're doing now with the Los Alamos National Lab, which sort of finds a nice middle ground between the flexibility of post-process visualization and the performance of in situ visualization by essentially allowing you to bracket your areas of interest. It derives from the observation you can generate a lot of visualization pictures for the cost of writing out a time step. So rather than generate a single picture for each time step, you produce every picture that you might think you might need for that time step. And you store all of them because they're all going to be vastly smaller than the time step itself. And it's going to take far less time to do it. And then you can interactively manipulate those afterwards. And you can I wish I could show you a demo of this. I plan to show you a demo of this, but it's not working today. You can interactively explore that set of resulting data. You can move around in time, and you can move from camera to camera so that your image appears to rotate on the screen. And all this is from pre-recorded images. And so it gives you a nice sort of intermediate ground between in situ and truly post-processing interactive visualization. And I just wanted to tell you about it because I think it's such a cool idea. Okay, I'm sure this is a slide y'all have been waiting for all along. In summary, parallel visualization is only partly about compute power. I mean, everybody thinks these big computers have vast amounts of compute power and that's what you're really after. It's not. It's also about getting enough memory to run your application without going to and from external storage all the time. And it is about maximizing the speed. You can go to external storage if you need to. And those are the three keys to going parallel on these systems. And I also want to say that I/O really is the big issue, in my mind anyway. The I/O that your visualization, that a big visualization is going to do, is going to dwarf the rest of the computation. And so thinking about how you do the I/O correctly is the single biggest thing that you need to think about in order to build a system that not only can generate data effectively and fast, and visualize it later effectively and fast. So that's the single key point I want to leave you with in this whole thing. The last thing I want to say is that we're here and do visualization and help people with visualization projects and create visualization technology, and we're here to help in whatever ways you guys need. That's our reason for being. So with that, I'll call for any questions. And if there are no questions, which I'm going to be very disappointed if there are none of, we will move on to take another break. Can never have enough breaks. And then I'll get some of my colleagues in here, and we will do hands-on, any questions or anybody want to go through any of the examples or anything with a little hand-holding, we would be happy to help. Okay? Be back in a little while.